And then we could expand the system to look at the energy inputs. And as you've heard from Javier, 80% of the cost of ammonia is the cost of natural gas. This chemical reaction, this single chemical reaction, uses about 2% of the total annual energy supply. And that has real implications for society. So if we look at some data which shows natural gas and oil, and this is the cost of those commodities, nitrogen fertilizers are the single largest operating cost for many farmers around the world. And we had spikes in nitrogen fertilizer costs in 2008 and 2011 because of the cost of natural gas. And the implications of those spikes can actually be traced fairly significantly to some global events that relate to what happens when populations now have a scarcity of food. So this Haber-Bosch process, depending on methane as an input, very, very real implications for one of those UN Sustainable Development Goals. And then, of course, that ammonia is used through the cycle of the Oswald process to produce nitric acid and ammonium nitrate. And we do that for intended uses. We do that so that we can produce fertilizers. And 80% of the ammonia that's produced goes into fertilizers, largely in the form of ammonia, urea, and ammonium nitrate. And then 20% is used for all sorts of other things, from pharmaceuticals to materials, including materials to capture carbon dioxide from the air with the form of amines. But then not everything from ammonia and the ammonium nitrate leads to intended consequences. We also have unintended consequences. And those unintended consequences include health effects of reactive nitrogen, too much fixed nitrogen, but also, of course, eutrophication. And you have here what happens when phytoplankton bloom as a result of far too much reactive nitrogen going into the ocean off the coast of Florida. So let me put this together now. Here's the system, starting with what we usually teach, and zooming out and looking at the other elements to that system that we'd like to help students see if we think about this as in the context of a system. And then, of course, we can zoom in again and look at one part of it, but at least students now see the whole first. And so if we have the different subsystems shown here, along with the intended and unintended consequences, now it's possible for us to see some of the things that emerge, the emergent phenomena, and I will end with this. Let's take that system of the Haber-Bosch process and think about the implications of that for these two sustainability agendas, for the planetary boundaries framework and for the UN Sustainable Development Goals. So we look first at the planetary boundaries. This is one of the two Earth systems, which is in the red, which has far exceeded the planetary boundary that's been set. The planetary boundary, which is the amount of industrial and intentional biological fixation of nitrogen, has been set at 62 teragrams of nitrogen per year, and we're almost 3 times that, 2.5 times that, 150 teragrams of nitrogen per year. And so that boundary has been exceeded, and the unintended consequences of that are very significant. But if we think of this as a system, of course, the planetary boundaries framework is a system in itself, and the amount of reactive nitrogen does not only affect that planetary boundary, but one can think about the implications of that for stratospheric ozone depletion, because nitrous oxide is one of the ozone depleters in the stratosphere. The implications for climate change. Nitrous oxide, again, is a potent greenhouse gas, contributing perhaps about 1/4 of the total change in radiative forcing of carbon dioxide since the Industrial Revolution. It's related to biosphere integrity. It's related to land use changes. It's related to fresh water availability. And so when we think about this as a system, this one chemical reaction has very, very significant implications for the planetary boundaries sustainability framework. And then let's look at what that might look like if we were to look at the biogeochemical flow of nitrogen and the UN Sustainable Development Goals. Well, of course, the most obvious one is that ammonia feeds people. produces plants, that feeds people. And so achieving zero hunger, incredibly important that we find better ways to produce ammonia. That's related to poverty, good health, well-being. Hungry people are not well, and they live in poverty. But of course, one of the other major uses in the last century of fixed nitrogen was the production of explosives, and probably 100 million people in the last century died as a result of nitrogen explosives. And for both of those purposes, fertilizers and explosives, we need energy, as we've discussed, with real implications for the UN Sustainable Goal number 7, and consequences of that production of ammonia, largely nitrous oxide production, which is done by microorganisms on legumes and other plants. They're able to take nitrogen, and in the process of nitrification and denitrification, they make laughing gas, nitrous oxide. Overproduction, implications for responsible consumption and production, life on land, life below the water, and clean water and sanitation. So this one chemical reaction, which we usually focus on as a very narrow reaction, major implications for the UN Sustainable Development Goals. So let me finish by just telling you what's next for the Systems Thinking project. We had a project meeting at the IUPAC Congress in Paris a few months ago, and future directions for the project have been set out by several colleagues on the project, Mary Kay Orgill, Felix Ho, and Alison Flynn. And it's very difficult to change the way educators teach and to change curriculum. The planet is accelerating these parameters. The great acceleration is going up exponentially, and educational systems change at the rate of glaciers moving. It's very difficult. It's very, very slow. And so we've identified the things that are needed if systems thinking in chemistry education is to take hold. And one of them, of course, is we have to tie this, ground this in learning theories, so there's evidence that systems thinking actually can work in the teaching of students. We need to connect to curriculum and program standards. We need to define learning outcomes for students based on systems thinking, activities and assessments aligned with learning outcomes. If you have a new approach and then the final exam is exactly the same as it used to be for 30 years, then of course students very quickly will learn this other material is not really very important. Training opportunities, and we'd like to create a virtual user community. And of course, we need to do some chemistry education research to provide the evidence for a pedagogical approach that can actually make a difference in student learning. And this work, including examining who might benefit most from a systems thinking in chemistry education approach, is forthcoming in one of the issues of the special issue of the journal on future directions for systems thinking in chemistry education. So what I've tried to do today is to give you an introduction to systems thinking in chemistry education, hopefully asking you to think about the chemistry education that you were taught with, or perhaps that you currently teach, and to examine whether there are ways in which systems thinking will allow you to help your students see the whole, to understand how relevant the chemistry they're learning is to emerging global challenges. I hope I've convinced you to think a little bit more about the molecular basis of sustainability. It would be wonderful if students coming in to university, coming into secondary school, would see that when they go home and talk to their parents, they say, I learned how important chemistry is to contribute to sustainability on our planet. I've given you some examples of some tools that can be used to do that, and then an idea of where the project's going. And if any of you are interested in being involved in the project, I'd really like to ask you to contact me. And I'd like you to think about the time frame. So we celebrate the 150th anniversary of the periodic table. We don't have 150 years. We don't have until St. Petersburg 300 years after Mendeleev to tackle these sustainability challenges. We have maybe 30 years, maybe 20 years, and we have to make progress, and chemistry has to be a central science contributing to that. We won't do that as a profession of chemistry without changing the way we educate. So let me acknowledge the Congress Organizing Committee, thank you for the invitation to present here, but thank you even more for featuring chemistry education and sustainability on a plenary forum for this Congress. I think it's incredibly important that that was done. I'd like to thank the members of the STICE Project Steering Group. This is at our group meeting a year ago in Australia. And Stephen Matlin is my co-chair, and IOCD has become involved in supporting the project. Tom Holm, whose work I featured today, and then Felix Ho and Mary Kay Orgel and Allison Flynn have done the work on future directions. And the American Chemical Society Green Chemistry Institute, Jenny McKellar and her colleague David Constable have made seminal contributions to the project. Spasiba.
Now I'd like to introduce the next plenary speaker, Dr. Peter Mahaffi. He's a professor of chemistry and co-director of King's Center for Visualization in Science in Canada, which provides digital learning resources used by, well, over 250,000 students, educators, and the public from more than 100 countries each year. Research and professional areas of the Dr. Peter Mahaffi includes chemistry education, system thinking in chemistry and education, visualization in science, public understanding of science, climate change science education, and organic chemistry, reaction mechanism, photochemistry, matrix, isolation, spectroscopy, and reactive intermediates. His professional service includes co-chair of Campus Alberta Quality Council, charter member of Organization for the Prohibition of Chemical Weapons, temporary working group on education and outreach. This organization received the Nobel Peace Prize in 2013. Editorial Advisory Board of Journal of Chemical Education. Past chair, International Union of Pure and Applied Chemistry Committee on Chemistry Education and member of IUPAC Bureau. Editorial Advisory Board, Chemistry in Context. Charter member, International Council of Science, Committee on Freedom and Responsibility in the Conduct of Science. American Chemical Society Presidential Working Group on Climate Science. International Advisory Committee of various